The remaining class also the same strength is there. Lanthanoid contraction. Right. Start with this one with what? Definition and everything. This is an important topic. Very, very important one. Now, in this, what we discuss about here, the difference in atomic and also what here? Ionic radii. In which elements? Inner transitional elements. Here, inner transitional elements means lanthanides and also what? Actinides. They comes under what? Actinoids. They comes under all what? Inner transition elements. 4F series and what? 5F series. All these comes under what here? Inner transitional elements. Now, in this differentiating electron, that means the last electron in the inner transition element, 4F and 5F series are called what? Inner transition elements in which differentiating electron will enter in which orbital? 4F and 5F orbital. If it enter 4F orbital, they comes under as a lanthanides. If you take what 5F series, they comes under. What is the meaning of Lanthanoid contraction? Very simple. The decrease in the size. The decrease in size of which elements here? Lanthanides, isn't it? The decrease in the size of lanthanides is generally called what? Lanthanoid contraction. Okay. Some exceptions are there. There are what europium and yttrium. There are exceptions. Leave it that one exceptions. Simple thing. The decrease in the size of the atoms or ions of lanthanides, isn't it? With increasing atomic number. ये सारी चीज बोलने की जरूरत नहीं. Simple thing. The decrease in the atomic size of lanthanide elements is called what? Lanthanoid contraction. Now, what is the reason behind this one? If you observe what happened here, the element is starting from lanthanide here, like cerium, isn't it? To what actually? Lutetium. Now here to here what happened? The size what happened here? Decreasing. The size what happened here? So this is in terms of, you see, observe atomic number 57 to what? Up to what? 72. Isn't it? What is happening there? Up to here. What is happening here? Size what here? Decreasing here. Now this is what actually ionic radii. What is the difference between the two graphs here? These are the atoms actually. These are the atoms. Okay? Elements. Now here in this one, these are ions. Lanthanum plus 3, cerium plus 3. Now here what happened? Lutetium plus 3. Now lanthanum to lutetium plus 3, we don't have any exceptions here. It is continuously what happened? Decreasing. So when you take in terms of ionic radii, if you take ionic radii, what is the meaning of ionic radii? Radii of ions. Lanthanum plus 3 to lutetium plus 3, what is happening? Continuously it is decreasing. But in case of what atoms if I take, like lanthanum, cerium, in terms of atoms I take, europium suddenly increasing, yttrium is also suddenly increasing. This is for what actually atomic size it is. Two exceptions are there in this one. One is europium, other is what here? Yttrium. Because of repulsions, electronic repulsions, what happens? Suddenly atomic size increases there actually. Now let me see what is the reason behind this one. The reason is what? Screening effect here. Because of screening effect, because of poor screening effect, isn't it? This is happening actually. So if in examination, if they ask what is the reason for the Lanthanoid contraction, you have to say because of what? Screening effect. Then what is screening effect here? What is the meaning of this screening effect if you observe what happened? Now the decrease of attractions of a nucleus over the valency shell by the inner core electrons is called screening. This is the definition actually. The decreasing of attractions, nuclear force of attractions over inner core valence electrons by the inner core electrons actually. Let me discuss this one. How to explain this one? I will take beautiful example. See. Now, if I take what happened, here I will take. Here let me take. Now, in this actually I have taken the nucleus. Okay, this is the nucleus. And here, first orbit, second orbit, third orbit, fourth orbit, fifth, and what here? Sixth. So if I take what lanthanoids I will take. What is the configuration? We are going to get 4F1 to what? 4F14. Next, what happened? 5D1, 6S2. This is the configuration, correct or not? Isn't it? This is the configuration. Now here you are having 6S2 electron, I'm writing. This is the sixth orbit, 6S2. And this one is what? 5D1. Okay. And this one is what? 4F1 or 4F2, whatever it may be. This will be what? 3D. This will be what? Something third orbit, second one, first one. So there are 6 orbits are there. Now here nucleus, this is the nucleus, positive charge. Okay. And this is what? Negative charge. The electrons are negative charge. Now this nucleus attracts this valency electrons readily. Because wherever your electrons are there, the nucleus compulsory attracts the electrons, isn't it? Wherever you're having electrons, that can be attracted by whom actually? Nucleus. But actually what is happening here, if you observe here, if you have any electrons here, if you have some electrons here, okay, you have any electrons here. Now these inner electrons will shield the outermost electrons from the nucleus. Outermost we are having 6s2 electrons. But inner electrons are there, inner means what? Which are having what? In the n-1, n-2, n-3 orbits. That inner electrons will shield outermost electrons. They keep away the outermost electrons from the nucleus. Isn't it? This is called what actually? Shielding effect. Because of the shielding effect, always what happen? If you have shielding effect, what happen? The atomic size or size always what happen? Increases. Okay. Whenever if you have shielding effect is there, size always increases. By increasing here, because you observe here, these inner electrons, isn't it, are making the outermost electrons away from the nucleus. Why? Because of this inner electrons, no. Because of this electrons, no, inner electrons, they're enabling the outermost electron, valence electrons from attracting from the nucleus. Now nucleus is unable to attract the valence electrons. For example, a teacher is there. Okay, first bench is there, second bench is there, third bench is there. Teacher is sitting here, something, isn't it? Now, because of this middle benches, what happened? A teacher cannot observe the last bench students. A teacher cannot observe the last bench students. Why? Because they are away from the teacher, and the middle students, what happened? The tall persons were sitting here. So that is the reason what happened. The teacher unable to concentrate on the last bench. So this is what actually I'm calling screening effect. Because of this, what happens? Size will increases because the nucleus losing the attractions from the nucleus. The nucleus losing the attractions from the whatever electrons. So the valence electrons. These valence electrons are unable to, isn't it? They are not under the control of what? Nucleus. 6s2 electrons are unable to attracted by what? Nucleus. That is the reason what is happening here. They are moving away from the nucleus. When they move away from the nucleus, what happens? Size increases. So leave it the confusion. I'm saying only simple sentence. Screening effect will increase the size of the atom or ion. What is screening effect? Shielding the outermost electrons by the inner electrons is called what? Screening effect. Okay, shielding or screening of outermost electrons by the inner electrons is nothing but called shielding effect. So shielding effect is high, size will increase. Here what I'm saying here, poor shielding effect here. The thing is what? Poor shielding effect here. Okay. What is the poor shielding effect means? What happened? Again, I'm drawing this diagram actually. First orbit, second orbit, third orbit, fourth orbit, fifth orbit, sixth orbit, and seventh orbit. Now 6s2 electrons are here. Now this is what? 5d1. This one is 4f1 to 14 something. Now these 4f electrons, isn't it? They are actually unable. The screening effect of 4f orbital will be very, very less because of their peculiar shape actually. Because of their peculiar shape, what happened? They cannot screen the 6s2 electrons. That is the reason the nucleus easily attracts what? Something, for just imagine 4f is there, something. Just imagine that. Now 6s2 electrons are readily attracted by the nucleus. When 6s2 electrons are readily attracted by the nucleus, what happen? The size, what happen? Compress, decreases. That is not happening. That means what our shielding effect is not happening actually. So if you have shielding effect, what happens? 4f electrons definitely will screen outermost electron. So because of poor screening effect of f orbital, because of their peculiar shapes of double dumbbell, fourfold double dumbbell shape here, fourfold shape actually, that is the reason what happened. They cannot do the screening effect. So with simple things, what we can say, Lanthanoid contraction definition I can give like this: the steady decreasing of atomic size of what? Lanthanoids due to poor shielding effect of f orbitals is called Lanthanoid contraction. So definition is very, very important for you. So what you write in the definition, again I'm repeating, the decrease in the size of lanthanides due to poor shielding effect or poor screening effect by the f orbitals is called Lanthanoid contraction, isn't it? This is the reason actually. Now, what are the consequences for what? Lanthanoid contraction. That means because of this Lanthanoid contraction, what happens actually? So, what is the result of Lanthanoid contraction? Let me see first of all the simple chemical properties here. Simple chemical properties, so similar chemical properties here. Okay. So, same properties they are exhibiting. But for example, let me see one example here. Lanthanides, if you observe, cerium to lutetium. Okay, cerium to lutetium. Now, there are a number of elements are there. Cerium, isn't it? Sodium, niobium. There are all these elements will exhibit what? Similar properties because they are closer size actually. So, whatever the elements present in the lanthanides, all the elements of the lanthanides are showing what? Similar properties. Why they are showing similar properties? Because their atomic size almost are getting similar because of lanthanoid contraction. They not actually should what happened? Because of lanthanoid contraction, the atomic size not neither not increasing what more or not what happened, decreasing also what very much actually. Almost are getting what small decreasing. In that case, what happened? The properties also what close like that. In that case, when they have similar properties, when they're having close properties, what happened? Separating the elements what very, very difficult. For example, the mixture is there. Cerium and praseodymium is there. Okay, cerium and praseodymium. Now these are belongs to lanthanides, and they are having almost a near size. Okay, almost a near size. That is the reason separating the praseodymium and cerium is very, very difficult for us. So that is the first consequence. In examination, if they ask what happened, because of lanthanoid contraction, it is very, very difficult to separate from the mixture. This is the first. Next, second point, if you observe what happened. Now, when you observe here, it's a series. If you observe what happened, I'm writing here from here. This is called 3D series in the 4th period. Okay, this is a 5th period and 5D series, 6th period, 6D series, 7th period, isn't it? Sorry, 4D series here it is. This one is a 4D series, this one is a 5D series, and this one is a 6D series. Generally, from 4th period to 5th period, size will increases. Everyone knows that one. Top to bottom, size of actually what happened increases. Normal thing actually. But from 4D series to 5D series, here from 4D series to 5D series, suddenly what happened? Size becomes same. Size gets what? Same. Gets same or somewhat decreases. Same or slightly what happened? Decreases. Slightly it will decrease. Similarly, what happened? From 5D series to 6D series. From 5D series to 6D series also, the size what happened? Suddenly what happened? Decreases. So what is you are observing here? Generally, when you move to what? Down in a group, when you move to down, what happens? Size should increase actually. But because of lanthanoid contraction, the size is getting same or somewhat decreasing very small actually. So when you observe what happened, I'm taking this series actually. I'm taking this series. Okay. In which scandium to yttrium, the size what happen? Increases, right? Size is what increases. But yttrium to lanthanum, if you observe what happens, size what happen? Not decreasing. It is what? Decreasing or somewhat same also. Similarly, lanthanum to actinium. Again, size what happened? Somewhat decreasing or remaining same. For example, if you take zirconium and hafnium, it's very, very important. Zirconium and hafnium, these two are having same size. In examination, they may ask, what is the reason? Why zirconium, Zr, why zirconium and hafnium, they are having same size? Because of lanthanoid contraction. Otherwise, niobium and tantalum, almost all they are having same size. What is the reason? Because of what actually? Lanthanoid contraction. So second point, what I mean to say in this case, because of lanthanoid contraction, isn't it? What is happening? Size getting what? Decreasing. Most of the case it may be same also. In which second point is what? From 4D series to 5D series and 5D to 60 series, size what happened? Decrease. Because of this, what happens? Zirconium and hafnium, they're having same size, isn't it? So this is about actually consequence if you observe this one. Now let me take this part. If you observe this one, yeah, zirconium, hafnium, niobium, isn't it? This niobium, tantalum, molybdenum, tungsten. They are getting almost all what? Same size in their groups here. Next, one more consequence if you observe, basic strength of the hydroxides. For example, if I observe what happened, cerium hydroxide, COH taken what? 3 times to what actually? Lutetium hydroxide taken 3 times. This as the size of the cerium, already I told you, cerium to lutetium, Lanthanoid contraction, size what happened? Decreases. Then covalent character will increases, then basic, generally what happens? Size decreases, no, covalent character will increases actually, isn't it? So covalent character and size both are actually inversely proportional, isn't it? So covalent character. So when covalent character increases, basic strength what happen? Decreases. Basic strength definitely depends upon ionic character. Okay. So what happening here? From cerium to lutetium, size what happened? Decreases due to Lanthanoid contraction. When size increases, what happened? The covalent character will increases. When covalent character increases, what happened? Ionic character decreases, sorry. When ionic character decreases, what happened? The basic strength, what happened? Also decreases here. So I'm writing here basic strength directly proportional to ionic character and covalent character, isn't it? Inversely proportional to what? Ionic character and size, isn't it? Size also inversely proportional to what? Covalent character, isn't it? This is about actually basic strength. So size is decreasing, ionic character is decreasing. When ionic character is decreasing, what happened? Basic strength is decreasing. Now, cerium hydroxide and lutetium hydroxide, which is having more basic character? Tell me better. Cerium hydroxide and lutetium hydroxide, which is having more basic character?
Lutetium hydroxide.
Basic strength is decreasing or increasing? Basic strength decreasing or
Decreases.
then which is having more basic character there?
Cerium.
Cerium hydroxide is having strong basic character. If you start from lanthanum also, you can start lanthanum hydroxide, isn't it? Cerium hydroxide, sodium hydroxide, like that we can write actually. So the first one will have more basic character when you compare with second one. Second will have more when you compare with third one. Actually. So the third one also very, very important for examination point of view. In math for multiple choice questions, you may get this type of questions, which is the correct order of what? Basic strength of lanthanide hydroxide. So from lanthanum to what? Lutetium or cerium to lutetium, the basic strength is decreasing because of lanthanide contraction. Understood here? Now you observe here this one. Barium hydroxide is mostly basic, while lutetium is the least basic, isn't it? So next, this is the inert pair effect also there. That is because of 6s2 electrons are no. So they are actually near to the nucleus. Because of Lanthanoid contraction, what happens? 6s2 electrons are readily attracted by the nucleus. They're unable to generate, remove. So they are unable to participate in the bonding. So here I can write actually inert pair effect means non-participation of which electrons? Ns2 electron. That means 6s2 electron. Now 6s2 electrons are attracted by the nucleus because of poor shielding effect. No, that is the reason 6s2 electron never participate in the bonding readily. Therefore, they are called inert pair effect. That will get in the 12th class actually. Can you give answer for this one? Is it possible for you? Too fast. Attraction of nucleus over the valence shell by the inner electrons. Which one? Screening effect, right? So remember this one, this point. Remember this point, very, very important actually. Why does the separation of Lanthanoid elements difficult? Tell me. Why does the separation?
They have similar properties.
Because of Lanthanoid contraction, the atomic
Similar properties, sir.
The atomic size getting almost all near or decreasing. Therefore, they are getting similar properties, isn't it? So the explanation for this one. Ionization enthalpy. Just I will take the definition only, so that tomorrow we'll complete this topic actually. So just I will finish what happened. Only the definition of ionization enthalpy. So to remove the electron, generally whatever the energy is required, no, that we call generally ionization energy. See, for example, I want to remove the electron like this. For example, some nucleus is there. Okay. Now first orbit is there, second orbit is there, third orbit is there. Here some electrons are there. This is called valency electron. This is called what? Valency electron, outermost electron. So generally removing valence electron is very simple, very easy when you compare with inner electrons. Now to remove this electron, we have to overcome the nuclear force of attractions. Okay. So how to remove the electron? First of all, you have to overcome, you have to remove the attractions from the nucleus. Then only we can remove the electron from the valence shell. So what amount of energy is required to remove the electron is called what? Ionization enthalpy, isn't it? Understood the definition? Very simple. The amount of energy required to remove electron from valency shell is called ionization enthalpy. Now, in this case, two things are very, very important. Before what happened, removing element. For example, X is there. Okay, X is there. Now, X, I am removing electron from this one. Okay, plus 1 means I have removed how many electron here? Only 1 electron. So before removing that electron, this X atom must be in gaseous state, okay, and also in the neutral nature. It should be neutral atom, must be neutral atom. So what I can change the definition now? The amount of energy is required to remove an electron from a neutral gaseous isolated atom. A neutral gaseous isolated atom is called what? Ionization enthalpy. Okay, the amount of energy is required to remove electron from outermost shell, mostly binded electron. Which one? Valency electron. Which electron we are removing? A mostly binded electron or valency electron. From where we are removing? From neutral isolated gaseous atom is called what? Actually ionization energy or enthalpy. Now what are the units for this one? Kilojoules per mole. General energy, how you just express actually kilojoules, kilocalories or electrovolts. So these are the generally what some conversions actually. 1 electrovolts actually is equal to 96 kilojoules or 23 kilocalories here. So this, if you remember what happened, better for you, because we can change that units also. This is the, see, whatever the definition I given, if you observe. This is the first ionization energy. What is the meaning of first ionization energy? Removing the first electron. Second ionization energy, second electron, like that. So the minimum energy, you observe here, the minimum energy required to remove electron from outermost orbit of isolated gaseous neutral atom is called what? First ionization energy. See, whatever underline which are important. Minimum energy required to remove the electron from the outermost orbit of isolated gaseous neutral atom is called what? First ionization energy. You observe here, this is the isolated neutral gas atom. Last one electron, the first electron, you are getting a monovalent ion. You are going to get a monovalent ion actually, isn't it? This is about the first ionization energy. If you want to write second ionization energy, how to write this one? Remove electron, second electron from where? Monovalent atom. Okay. So remove the second most loose. Now you remove the second most loosely bounded electron, isn't it? Second most loosely bound electron from where? Mono positive or uni positive. So after removing first electron, you can remove second electron. That is called second ionization, isn't it? By using something monovalent, now converting into your divalent. You have removed now which electron? Second electron. Okay. Now in general, what happened? Energy is always required. In any case, if you want to remove electron, we have to supply some energy. So that generally we call endothermic process. Supplying of energy generally is called what? Endothermic process. And enthalpy will be always what happen? Positive. Delta H is always will be positive, because whenever you are supplying energy, it means endothermic, delta H is equal to positive. In this way, what happened? We can write third ionization energy, second ionization energy, third ionization energy. Like that, we can write n number actually, isn't it? So this is about actually what? Ionization enthalpy definitions here, right? How many there in the class now?
29, sir.
Only 29. In the remaining class also same strength is there or full strength is there?
Sir, usually these many people only join the class, sir.
Remaining they are not joining in the remaining class also.
Sometimes they join and sometimes they don't join, sir.
So 32 are there.
I'm getting only frequently, I'm getting only 41 to 42 students are joining. In the last class, from up to last class, what happened? Seen what? Only 40 students. Have class tomorrow morning also?
Sir, tomorrow we have chemistry in afternoon only.
That is, I know, 1 to 1:45. Tomorrow, when you are having some classes you are having, not that is not timetable, not timetable, not general you are having. What time you are having classes?
So tomorrow 10:45 to 11:45 we
Tomorrow
have
having
bio
10,
class.
what class?
Sir, bio 10:45 to
10:45.
11:45.
Okay. Tomorrow I will take at 1 o'clock. Okay. At 12 o'clock, what class you are having?
Maths.
Sir, no, we are not.
According to timetable it is.
Maths.
Okay, okay. So tomorrow I will take at 1 o'clock only. Normal time only I will take. Okay, had your lunch before whatever the class what happened at before 1 o'clock. Had your lunch. Okay. Now you can leave. If you have any doubts, you can stay with me. Otherwise, you can leave now.
Thank you, sir.
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 Thank you, sir.